the integral from a to b of f of x with respect to x is equal to, we're going to say capital F, the antiderivative of lowercase f, the integral. Either integral or antiderivative, whatever blows your hair back. It's this evaluated at the limits from a to b. That's fancy notation. We can also say that this is f of b minus capital F of a, where capital F of x is the integral or the antiderivative. Right? These are inverses. It's the opposite of the derivative. Derivative of f of x. We can even say such that capital F prime of x is f of x. The derivative of the antiderivative is the function. I'll let you marinate. I'll let it simmer. Put it on the back burner. Just let it sizzle for a little bit. And we could call this thing here a definite integral.
What's the integral?
The integral is the antiderivative.
What?
So when we take the derivative, we find the rate of change of a thing. Remember we said the slope of the tangent line?
What is it in this equation?
The integral is capital F. So the regular function is lowercase f. The integral or the antiderivative of this is this. So this symbol means take the integral of. So this symbol says take the integral of f of x, and you're going to get the antiderivative or the integral, capital F.
An integral is the area under a curve.
Yes.
Okay.
So remember we found the area under the curve of velocity was distance.
Aha.
Can you do that notation?
That really, yeah.
Wait,
really
what did you
helps.
just say?
All right, let me repeat it. Yesterday we saw that the area under the velocity curve was the distance, and I just told you, that when you have the distance function and you take the derivative, you get a velocity function, and you take the derivative, you get an acceleration function. So derivative will take you this way, and the antiderivative will take you back up the chain of command.
So antiderivative and integral are synonymous.
Yes.
And can you do that notation in front for like a value instead of a function?
Yes. You can
So
take the integral
integral
of 5.
Okay.
Integral equals antiderivative.
Just like you can take the
Then what's the
derivative
point?
of 5, you can take the integral of 5.
Then, so just the reason you put that capital F with the straight line instead of the curved line?
So we did the integral of this
Yeah.
and got capital F,
Which is the antiderivative.
the antiderivative, but we have to evaluate it at its endpoints and subtract them. The integral at the end minus the integral at the beginning gives us the answer to that. So a definite integral has start here, stop here at definite points, and you get a specific answer. You get a value. A definite integral will give you a numerical answer. Definite integral, numerical answer. That's good. Then we should write that. Equals numerical answer.
Just one question. So integral and antiderivative are the same thing?
Yes.
Okay.
Integral Antiderivative. So a definite integral says I want you to find the area under the curve. So we should write that somewhere up here also. Area under the curve. So this is this here is saying find the area under the curve f of x in between x equals a and x equals b. And when you find that area, it's going to be a number like 128 or something. You're going to get a numerical answer on a definite integral because you're finding a specific area and boom, you got an answer. But then we can also take an indefinite integral, which is a general kind of thing. Kind of like when we took the derivative of a function, we got another function. We can take a general integral of a function and get another function. So that's the indefinite integral. And I'll write that here. Indefinite integral. And that, my friends, is the integral of f of x with respect to x. Notice I don't have any endpoints. So I'm not saying, specifically from here to here, find the area under the curve. I'm saying find a function that'll tell me the area under the curve anytime I want to.
So, English.
Okay, so you know how when we took a derivative, we got a function, f prime, that told us the slope anywhere we wanted the slope of the original function. So this is a lowercase f. Now this matters. So if you've been using lowercase and uppercase, f's all willy-nilly, like whatever, now get your mind right. Lowercase f means the function. Capital F is the integral or the antiderivative. So the integral, generally, indefinitely, from no place to no place, of f of x with respect to x is just this function here, without all this evaluated at certain places.
Wait, the derivative?
No, that's
The integral.
That's what that means. Gotcha.
Yes.
Gotcha.
like, what's the derivative of f of x? Or I mean of x squared, sorry.
X something, 2x?
Yeah, and
Yeah.
so what's the derivative of x squared at 2?
Don't do this to me. 4?
Yeah. So that would be the
I
definite
need to-
derivative versus the indefinite derivative.
Hold on. I gotcha. Okay. Wait, but can you eventually get to a definite derivative?
Integral or derivative?
Whatever, Jason.
So this is super general. Let's start using some numbers, and then you're like, oh, word, I got you. So let's do that. Can we do
No,
that?
I wanted a definition for indefinite integral, or what it gives. I know, but what it gives in English. That's
So
all.
this gives me a numerical answer,
Yes.
and this gives me a function. I'm just going to say a function.
Okay.
I mean, it is a function such that the function's derivative is the original function I started with.
I'm not gonna write that.
Okay, but I mean, it's this. I'm not going to write this again. The antiderivative, if I take the derivative, I get the original function.
Okay.
So if I have a function,
Okay, cool.
I integrate it and then I differentiate it, I end up at the same place. They are inverses. They undo each other. They are opposites. So I can differentiate, then integrate, and get the same place, or integrate and differentiate. They cancel each other out and we get back to the same place.
Okay. I knew that was fake, but...
Okay.
Wait, distance, velocity, and then acceleration?
Yes.
Or velocity, distance, and acceleration?
Stop it. So distance. So I walk a distance.
Uh-huh.
The rate of change of my distance is the velocity.
distance, velocity, acceleration.
And then the rate of change of my velocity is my acceleration. It's all rates of change. And when we take the integral of a rate of change, remember we had the rate of change of oil leaking, liters per hour. We took the integral and we just got liters. It got rid of the time element. So it undoes a rate of change. Right? Because distance, we have a distance function, is in meters. We have a velocity function that's in meters per second. Then we have an acceleration function, which is meters per second, or meters per second squared. So rate of change, then a rate of change of a rate of change. And if we take the integral, we go backwards and we get rid of a rate of change and how much of the thing changed.